Okay, guys, we're going to start Chapter 5 today. Chapter 5 is titled Kinetics. When you look at what kinetics mean, it's a part of chemistry that studies the speed of chemical reactions. So I've got a few pictures on this slide that remind me of kinetics. For example, this car right here, guys, how long will it take for that car to look like the car on the right? Long time. Like, let's put a number to it. How many years would that take?
30 years, 40 years.
Yeah, this could take decades, right? This could take decades in order for a car to rust. So there's really slow chemical reactions. But then I've got a picture of the space shuttle here. Rocket fuel, how fast does it combust?
Within seconds.
Yeah, very quickly. And fireworks, how fast are they?
Very fast.
Very fast. So chemical reactions can be very slow, but they can also be very fast. So let's get started. I'd like you to have your guided notes out. It's Chapter 5 guided notes. Okay. This chapter is titled Kinetics. So I'd like to start with what the definition of kinetics is. So take a second and jot this down. Kinetics is the area of chemistry that studies the speed or the rate of chemical reactions. So it's a whole area of chemistry, and we're studying the speed, or you're going to hear this a lot, the rate of a chemical reaction. Like we just talked about, some chemical reactions occur very quickly. For example, explosives. They need to occur within milliseconds. That's what makes them explosive. They happen very quickly. But some chemical reactions occur very slowly. For example, rust, like we just talked about, iron forming iron oxide. This process where rust is forming can take years or decades in order to occur. Now, this might be the most important thing that I talk about today. Okay? The rate of a chemical reaction is determined by the activation energy of the reaction. So this whole idea of rates, how fast chemical reactions occur, is determined by the activation energy. And we're going to review a lot of the concepts from first year chemistry in the next few slides, but it's very useful. I think you'll start to remember it as we go through it. So let's get started. First thing we're going to review is this, activation energy. It's given this symbol E sub A. It means energy of activation. So the energy of activation is the minimum amount of energy that reacting particles must have in order to complete the reaction. I always like to use a matchstick as an example right here. If you look at this matchstick in my hand, I've got the reactants for this reaction. It's the wood and it's all the phosphorus in the tip of this match. How long will it stay as just the reactants? Forever, right? Forever. How do I form the products in this reaction, in this match reaction? I've got to give it the activation energy. Guys, how do I do that? Yeah, it's when you strike it across this friction bar, right? You're going to give it the activation energy. What, for example, if I give it this much activation energy, will it form the products down here? No. The minimum amount of energy is the activation energy. So you've got to give it at least this much energy. Now, what if I give it a whole bunch of energy? Will it form the products?
Yeah.
Sure. That's the minimum amount of energy. So if you get it up to there, it's going to form the products. So that's what activation energy is. Okay, we're going to review energy diagrams in the next few slides. In order for a chemical reaction to occur, the reactants must overcome this hill. This hill represents the activation energy. Now, the amount of the activation energy determines the speed of the chemical reaction. So how high that hill is is really what determines how fast the reaction will occur. Now let's make a prediction. What if the hill is huge? What if it's just a lot of energy? Fast or slow?
Slow.
The reaction is going to be very slow. What if that hill is really small?
Fast.
It's going to occur very quickly. Okay? So a large energy of activation equals a slow reaction. What if that hill is not so large? What if it's really small? Then it's going to be a fast chemical reaction. Okay, let's talk about a process that we talked about last chapter in terms of energy. We talked about diamond going to graphite. Diamond and graphite are made of carbon. Now, what changes diamond into graphite? Well, it's how the carbon atoms are arranged. But they're both pure carbon. If you remember from last chapter, this conversion from diamond to graphite was thermodynamically favorable. What I mean by that was delta G is negative. Is this a spontaneous process?
Yes.
Yes. That means it's going to occur on its own without outside help. That's going to happen. But when you buy a diamond ring, should you be worried that it's going to turn to graphite tomorrow?
No.
No. How come?
It takes a long time.
This process, even though it's favorable in terms of thermodynamics, it's going to take a long time. Like it says here, however, just because the reaction is spontaneous doesn't mean it will occur quickly. The activation energy for this reaction is very high, so the reaction occurs very slowly. So this hill is really high for this process. So if you buy a diamond ring, you don't have to worry. It's not going to turn to graphite overnight. Okay, let's review energy diagrams. From last chapter, a couple of terms. What does exo mean, guys? Exit. What does thermic mean? Heat. Okay, what does endo mean? Enter. What does thermic mean? Heat. Okay, so let me review the energy diagrams for a second. For an exothermic reaction, we see the reactants are starting up high, the products end down low. So what is my delta H value going to be here? Positive or negative? Right, it goes down, so delta H is going to be negative. Guys, can we destroy that much energy?
No.
Where does it go? You can't destroy it. You got this law of conservation of energy. You can't destroy it.
It goes to the surroundings.
It goes to the surroundings in the form of what, though?
Heat.
Heat. So do exothermic reactions make things hot or cold? Hot. So because it's releasing heat, this is going to make things very hot. Now let's go to endothermic. The reactants down here, the products end higher. So my delta H value is what? Delta H is positive. Now, can I just create that much energy? No. Where does it come from? It's absorbed. So heat is absorbed from the surroundings. Does that make things hot or cold? This makes things cold, right? Because we're taking heat away from the surroundings, which makes them cold. Now, that's just a good review, but let me ask you something about this chapter now. Which type of reactions, exo or endothermic, do you think happen faster in terms of their kinetics?
Exo.
If you're saying exothermic, you're right. How come? If you look at this hill, which one has a lower hill, guys? Exothermic. The hill is much smaller, so they're going to occur much faster. Okay, let's review another concept called, here with activation energy, we'll get to it. How do reactants overcome that activation energy? So for example, if I've got molecule A, and I'm going to mix it with some B, and it's going to make product C. How do I get the reactants here, A and B, to overcome the activation energy? That's my question. So if these are molecules right here, what do they got to do in order to react?
Combine.
They've got to
Mix.
collide. There you go. They've got to collide. So reactants must collide with each other in order to form the products. If I have A and B, guys, if A and B never hit each other, will they ever make C? No, they'll just stay as themselves, A and B. They will never make the product. So reactants must collide. They've got to hit each other. If you remember from last year, we talked about this. It's called collision theory. There's 3 parts to it, so let's review it now. Collision theory states that atoms, ions, and molecules must collide. They must collide in order to react. But just colliding is not good enough. They've got to collide. So it says here the reactants must have proper orientation. They've got to hit in proper orientation in order for the reaction to form the new bonds that are going to be present in the products. For example, if we have molecule A, which has 2 atoms of A, and molecule B, which has 2 atoms of B, notice the orientation or the way that these molecules turn does matter. They've got to hit each other so that they can form AB. So they've got to hit each other in the correct orientation so that a new bond can form here and there that are present in the products. Now, what if they hit each other and it's not in the correct orientation? It's not going to work. Then they just bounce off of each other. For example, in this chemical reaction where we have carbon monoxide, and let's say we reacted with this molecule here, nitrogen dioxide, those are my reactants, so they've got to collide. When they collide in the proper orientation, they make CO2, which is this molecule here, and NO, which is nitrogen monoxide, right there. Now watch what happens if the carbon from this carbon monoxide collides with the nitrogen. It's called an ineffective collision. What's going to happen is that they're just going to hit and bounce off of each other. There's no reaction. If you look at one of our products here, it's CO2. CO2 is right here. So notice what happens when this carbon collides with an oxygen. Then it kind of just stills that oxygen and forms a new bond. And this nitrogen monoxide is left by itself, so that's what becomes right there. So orientation does matter. They've got to hit with correct orientation as well. Okay, there's 3 parts to collision theory. We just talked about 2 of them. Here's the last one. Molecules must collide with sufficient energy in order to overcome the activation energy. So not only do they collide, they have to collide. And they have to collide with correct orientation. But they've also got to collide hard enough, hit each other with enough energy. So we call that sufficient energy to overcome this activation energy barrier. Okay? So for example, these 2 molecules here, they've got to hit, and they've got to hit with correct orientation. But what if they just kind of glance into each other in correct orientation? Are they going to react?
No.
They won't. They'll just bounce off of each other. Now, if you give them at least this much energy, then they will form the products. Okay? And so that's the last part of collision theory. And like it says here, if the reactants don't collide with sufficient energy to overcome the activation energy barrier, then no reaction will occur. Yeah, you might give it this much energy, but it's not going to form the products. Right? Okay, so let's summarize collision theory real fast. There's 3 parts. Number 1, the reacting substances must do what? They must collide. There's got to be some collision there. Okay, they got to collide. Step 2, not only do they have to collide, but what do they got to do? They must collide in the correct orientation. And then step 3, not only must they collide and collide with correct orientation, but now step 3, they've got to collide and hit each other with sufficient energy to overcome this activation energy hill. Okay. Okay, before we move on, let me just give you a pop quiz and see if you guys got this. If I got 2 energy diagrams down here, I'm going to title this first one A, and this one on the right, B. Okay? I want you to tell me which one is going to happen faster. Which reaction is going to occur faster? Is it going to be A, or is it going to be B? I'm going to try and draw them in the same spot.
Obviously, it's going to be A.
A or B is going to happen faster?
I could have told you
A. Very good. How come A is going to happen faster, guys? It's got a way smaller energy of activation here. It's way smaller. B, it's way larger. So A is going to happen faster. Now explain it to me in terms of collision theory. How come A is going to go faster?
They can glance off themselves more. They don't have to hit most.
They don't have to hit with near as much energy, right?
Yeah.
So are more collisions going to be effective collisions?
Yes.
Yes, and we'll form more products that way. So that's why it happens faster. Okay, let's talk about something that we did introduce last year as well. Called a catalyst. I think you guys are supposed to write down the definition, so here it is. A catalyst is a substance that speeds up a reaction without being consumed itself.
It lowers the activation rate.
Good. A catalyst is something that a chemist can put into a reaction and makes it go faster. But is it used up itself?
No.
No. A catalyst speeds up a chemical reaction by lowering what?
Activation energy.
It lowers the activation energy. So if you look at this energy diagram down here, I want to point out a couple of things. Does using a catalyst, now a catalyst is the dotted line, this red dotted line. So that's with a catalyst, is the red dotted line. Without a catalyst, it's this black solid line. Now, does a catalyst affect the energy of the reactants? Or are we starting at the same spot? Yeah, so it doesn't affect the energy of the reactants. It's the same. Does it change the energy of the products? No, it's still the same, right? But what does a catalyst do? It lowers the activation energy. Now the activation energy is much lower, which means more molecules, when they collide, are going to make collective or effective collisions and form the products. Okay, so I've got a couple of YouTube videos. Now this is of a student in this room doing a chemical reaction called the iodine clock reaction. Now the iodine clock reaction is a reaction where you mix two colorless solutions, and as the reaction happens, you're going to notice that it's going to change color. It changes color to this really dark, almost black color. What I want you to do is take a mental note when we watch these videos. This one here is without a catalyst, and the one that we'll watch later is with a catalyst. Okay? Make a prediction. Which one's going to happen faster?
That one.
Which is which one? You're predicting that the one with the catalyst will occur faster, and that's right. Now let's watch and see how much faster. Okay, now he's going to pour these solutions together, and then it goes to slow-mo, so it takes a while. So while he's mixing these two things, let me explain what's going to happen. Okay? You're going to see a color change happen at the bottom of this graduated cylinder. And the color change is going to be the start of the chemical reaction, and then we're going to watch the reaction happen. It's going to flow up the tube, but I want you to make a mental note of how long it takes it for it to climb to the top of the tube. Okay, so it's about to start, and you're going to see it start at the bottom of the graduated cylinder here. See it starting here? Okay, so make a mental note of how long it takes for this reaction to occur and go to the top of the graduated cylinder. Okay, so it looks like it's about done. How many seconds would you say that was? Maybe 5 to 10 seconds, right? Maybe 10 seconds. Now let's look at the same reaction done in the same graduated cylinder. The only difference now is that they have added a catalyst. So again, it's going to take some time. He's got to mix them. He's going to pour this into the graduated cylinder. But when it starts, make a mental note of how long it takes for the reaction to go to the top. Okay, so it's about ready to start. You're going to see it start at the bottom of the graduated cylinder. There it is. And it's already to the top. It's already finished. So it took only like 1 second. So you can see there, dramatic difference. With a catalyst, reactions occur much faster. Okay, but the question you might be asking yourself is, how does a catalyst make reactions go faster? So let's answer that question of how they work. Well, a catalyst will ensure that molecules collide in correct orientation. So it makes molecules collide with correct orientation. So less energy is needed. Enzymes, if you remember from your biology class, you probably spent a lot of time talking about enzymes. Enzymes are proteins that are inside of your cell. There's hundreds, if not thousands, of enzymes in your body, in each one of your cells, helping your chemical reactions occur faster. So what's the difference, guys, between a catalyst and an enzyme?
Isn't enzymes like biological?
Enzyme is consumed.
Nope. Here's the only difference.
It's biological.
Different names.
What's the biology?
One happens in living organisms. So an enzyme is a catalyst that you will find in a biological organism. So it's a living organism. Bio means life. So it's a biological catalyst. Does the same thing though. Catalyst enzymes, they do the same thing. Now, I've got a picture. I'd like to go through this diagram down here on the bottom. I would like you to watch very closely because this explains what they do and how they work very well. So if we have two substances here, two molecules A and B, those are my reactants. So I've got A plus B, and it's going to form the product AB. So we've got a synthesis reaction going on here. The product, you'll notice, is fused, and so we call it AB. If you go back to collision theory, what do A and B have to do in order to make the product? Well, they got to do three things. They got to collide, first of all. They got to collide with correct orientation and with sufficient energy to overcome the activation energy. So how does a catalyst work? Well, it makes A and B here collide in the correct orientation every time. So there's less time spent fumbling around between A and B and bouncing off each other in incorrect orientations. So an enzyme or a catalyst provides a surface for these reacting molecules to react upon. This surface makes them collide in the correct orientation every time. And so it brings these two molecules together. It kind of looks like a puzzle piece, but it makes them collide every time to make the product. So there's more effective collisions. That speeds up the reaction dramatically, as we just saw. So another point that I would like to emphasize with enzymes and catalysts. Did it change the enzyme doing that? No. Could this enzyme or this catalyst then be reused and help another reaction occur faster? Absolutely. So enzymes or catalysts are not consumed in the reaction itself. You can reuse them over and over and over again. Okay. Real quickly, this is an endothermic reaction, but here's how a catalyst would change the energy diagram. Does it change the energy of the reactants? No. Does it change the energy of the products? No. The only thing it does is lower what? What do we call this, guys? The activation energy, so it lowers it. Okay? Same thing with exothermic reactions. It's not changing the reactants' energy at all. It's not changing the product's energy at all. It's just simply making this hill much smaller, which makes reactions go faster. Okay, I'm going to end with this concept today. We're going to talk about the 5 factors that will influence reaction rates. There's 5 things that chemists can do to either make your reaction go faster or slow it down. So let's talk about them. Number 1 is the nature of the reactants. What do I mean when I say the nature of the reactants? Yeah, it's kind of the properties of the reactants. So gases in the so a substance in the gas phase will react much faster than a substance in the liquid phase, and liquids will react much faster than substances in the solid phase. So I'd like you to circle the gas phase here, gases. How come though? Why do you think gases react so much faster than solids? Yeah, the molecules are moving faster. If they move faster, will they collide more? Yes. Is there a better probability that they will collide with correct orientation? Sure. And with sufficient energy? Gases are moving around very quickly, so they're going to react fastest on average. Okay, but let's also talk about the number of bonds. We've learned about single, double, and triple bonds. Which ones will react the fastest? Single bonds. So I'd like you to circle them. Guys, tell me why. Why do you think reactants with single bonds react faster than triple bonds? Which one takes more energy in order to break them? Triple bonds take a lot of energy. Well, less energy is required to break a single bond, so they will occur faster. Does that make sense, guys? So that's what I call nature of the reactants, some of the properties of the reactants. Okay, the second factor is concentration. Concentration of the reactants. If you increase the concentration, do you think it's going to happen faster or slower? Faster, yeah. If you've got a more concentrated solution of your reactants, that reaction is going to happen faster. So the more molecules present, the more collisions. Think about it in terms of collision theory. Now you've got more molecules, better chance they're going to collide and form the products. And so the faster that reaction will occur. All right, temperature. This is a big one. Okay? Make a prediction. Will the reaction go faster if it's hot or cold? Hot is the correct prediction there. So the temperature increases the speed of collisions. Now molecules are just moving faster. They're going to collide more. They're going to collide with more energy to overcome the activation energy. So here's a rule of thumb. It's not true of every reaction, but it's pretty good generalization. A 10 degrees Celsius increase in temperature will double the reaction rate. So if you want the reaction to go twice as fast, what do you got to do? Increase the temperature by 10 degrees. It'll go faster. Now, I always like to talk about this as well. The opposite of that is true. So if you do a chemical reaction in a cold environment, will that reaction go fast or slow? Slow. Yeah, if you decrease the temperature, you're going to make that reaction much slower. And this is the real reason we have refrigerators. I guess it does chill things, but the real reason is to decrease the temperature so that the food that you put in your refrigerator doesn't go through those reactions that lead to spoiling the food or rotting the food so quickly. It slows it down. Here's a quick and easy experiment to try. Buy 2 gallons of milk, put one in the refrigerator and one on the counter. Which one are you going to want to drink in a week? Yeah, the one in the refrigerator. It's slowing down the reactions that leads to spoiling the milk. Okay. Okay, number 4, surface area. Surface area is a big point on how chemists can influence the speed of the reaction. The more surface area will lead to faster chemical reactions. So we want to increase the surface area of our reactants. So what's going to burn at a faster rate? A big lump of coal? Or let's say you take that lump of coal and crush it into very fine particles. Which one's going to burn faster? Yeah, the one that has more surface area. So if you crush it up, it's going to react much faster. Like it says here, powdered sugar is going to react faster than granulated sugar, but granulated sugar will react faster than sugar cubes. Think about it in terms of collision theory. If it is smaller, which means you have a higher surface area, now there's more reactants that are free to collide with other reactants and form the products. Okay, last one is a catalyst, which we just studied. A catalyst increases reaction speed by lowering activation energy. So it makes the reaction go faster by lowering the activation energy. So there's 5 ways, guys, that a chemist can manipulate a reaction to make it either go faster or slower. This is going to be tested a lot. You've got to know these 5 ways to influence the speed of a chemical reaction. Before we finish, I want to just review everything that we just talked about in this lesson. What does kinetics mean? That's what this whole chapter is about. What is kinetics? It's the speed of chemical reactions. We talked about what determines the speed of a chemical reaction. What really is it that determines the speed of a chemical reaction? It's called what?
Activation.
Yeah, the activation energy. Guys, if this activation energy is small, reactions will occur faster. If this activation energy is huge, reactions occur slower. Okay? We also talked about a way to lower the hill here. How do we lower the activation energy? We introduce a catalyst. Okay, introduce a catalyst. We'll make it much smaller and the reaction occurs faster. Okay, then we just finished with 5 ways that chemists can manipulate a chemical reaction to make it occur faster or slower. What's number 1? Nature of the reactants. What reacts faster? Solid, liquid, or gas? A gas will. Single, double, or triple bonds? Single bonds react faster. Okay, then we talked about temperature. If you increase the temperature, what does that do to the rate? You increase the rate of the reaction. Now, there was a rule of thumb. For every, how many degrees Celsius? 10 degrees Celsius, you can do what to the rate? You can double the rate. Okay? And that's true if you cool it down 10 degrees, you're going to make that rate slower. Okay, then we also talked about surface area. Do you want high surface area or low surface area if your goal is to make the reaction go faster? High surface area increases the rate. How come? Well, now you've got more surface of the reactants that are available to collide and form the products. Okay, we also talked about one other way. What was it? Oh, 2 other ways. Concentration. Do you want it to be concentrated or dilute? Concentrated. Yeah, if you got more particles, they're going to collide more, they're going to form more of the product faster. And then finally, a catalyst, right? Okay, before we stop this video, in your student workbooks, there's a worksheet that I would like you to go over. It's called the Introduction to Reaction Rates Worksheet. Now, I only want you to do the first half of that worksheet. Again, it's called Introduction to Reaction Rates Worksheet. So please get that 1 page done, the first half of that worksheet done, and hopefully this video helped.